No, it's not going to be too long.
He's actually currently observing. Just as press conference. So he hasn't actually. Oh yeah, so he did the last 5 days. He just did go out, but now he's.
And he said that if anybody like says anything that doesn't make sense, the crap out of him like yeah.
Where is he? I was there.
Where?
He also did me, but.
No, I've only been in Delhi, but I visited India a lot. So my sister went to university there. And I know we it's hard to be like
I remember it.
no meat, no
This is the cheap marquee. That's the fun thing. Sticker book. Yeah, honestly speaking, I guess I'm just vegetarian. Vegetarian. I think I like to share much more. This is like your
Okay, let's get started. So this week we have the pleasure to have with us Chandong Park from Korean Institute for Advanced Study. So Chandong started his career in Princeton where he got his PhD. He then went to Caltech for a postdoc, went back to Korea at the National University.
Seoul National.
Seoul National University for a first position, and 5 years ago he moved to the Korean Institute for Advanced Study. He has been working on the CMB, on large-scale structures, and lately on galaxy evolution. So he's going to tell us today about galaxy interaction, large-scale environment, and galaxy properties.
Thank you. It's great to be here to have a chance to give you a talk. I'm particularly happy to visit Toronto in this best time of the year. Today, I'm going to present some of my work on the galaxy-galaxy interactions. This work was motivated by the current ideas of galaxy formation, which says the structures form hierarchically. So the small structures form first, and they merge to form larger structures. And therefore, to understand structure formation, we need to understand what happens when galaxy interacts and when they merge. But actually, do we really understand the consequences of the interactions between galaxies and between galaxy clusters and the evolution of merger products? For example, when galaxy interacts, is the star formation activity enhanced? Or how the structures change and how morphology change? And if they are changing, what are the physical mechanisms behind it? And all these, even though there have been many studies before, not all of them are answered yet. And for galaxies in clusters environment, it's not sure what these galaxies are actually interacting with. And the morphology density relation and morphology radius relations, we are not sure whether any of them are fundamental. And it's very important to know what happens when galaxies merge, but there's only a very simple idea from theory or simulation saying that the two spiral galaxies can merge to form an elliptical, but other than that, there is not much known. And there are many development recent days, but it's still not clear what happens after galaxy merge. So this is the topic. I'd like to show some evidence for the importance of galaxy-galaxy interaction in the evolution of clusters and in the evolution of galaxies in general. So I'm going to show some observational findings from the galaxy interactions in general environment and in cluster environment. And I'd like to summarize my key results with some interpretations. first, before I go to the galaxy-galaxy interactions in general field, the first thing to do is to make the morphology classification of galaxies, because we find the galaxy interactions can be very different for different pairs of morphology. So we first have to know the galaxy morphology, and to get accurate results, we have to deal with many hundreds of thousands of galaxies. So the visual classification is certainly not possible. So we developed an automatic morphology classifier, which uses the U-R color and G-I color gradient and I-band concentration index. So we use 3 parameters to classify galaxies. And the reliability and completeness of the result, which is about 90%. For example, we have training set here. So the reds are the early type galaxies, and the blue crosses are late type galaxies. And they distribute in this 2-dimensional plane in this way. The early type galaxies has the sequence like this, and the late type galaxy has the sequence like this. So they are more or less well separated from each other in this color and color gradient space. Then, in color magnitude space, we draw a line and make a visual inspection for early type galaxies bluer than this line. And we make also the visual inspection of the late type galaxies rather than that line. So we make some corrections. Usually 5% of galaxies are wrong. The classification is wrong. So after this, we have the reliability greater than 90, down to 17.6 in R-band pattern magnitude. If we had better image, of course we can apply different classifier, but given the SDSS images, this is about the best we can do. So right now, the final DR7 is released to collaboration, which is going to be released to public on October 31st, which is close. We applied this automatic classifier to all galaxies. There are almost 0.9 million galaxies with spectra in the final data. But there is a New York University value-added catalog with bright galaxies included. There are 590,000 galaxies with redshift there, and all of them are classified. So it shows some galaxies in this 2-dimensional plot. The color is not very good here, but it's the blue early type galaxies. And the late type galaxies, as they move down along this sequence, they first develop the blue color at the outskirts of disk, so that the color gradient becomes much more negative. Then as they become bluer, the center becomes bluer. And finally, the color gradient is inverted, and now the center is more bluer at the end. Whereas the early type galaxies, as they move along this early type sequence, they immediately becomes positive in color gradient. So they make this sequence. Some results. In some cases, like these galaxies are classified as early type, and there are some passive late type galaxies like this. Anyway, so after we make the morphology classification, then we move to study the galaxy interactions. We use Sloan Digital Sky Survey. Now this gap is filled in DR7. So we are working hard to finalize the BR7 data. But today, my result is based on BR4 plus, which is almost BR5. And so this is redshift versus absolute magnitude in the R band, and this cut is due to the apparent magnitude limit. And the galaxies are distributed over here, and we make a volume limit sample of galaxies like this. It's limited by the distance and also the absolute magnitude. So I have a complete homogeneous set of galaxies above certain absolute magnitude. I should explain how the nearest neighbor is defined, but if you ask, then I answer. The first parameter we measure is the early type fraction. So you choose a galaxy randomly and ask which morphological type this galaxy belongs to. So that's the probability that a randomly chosen galaxy is an early type. So that's the y-axis. And the x-axis is the distance to the nearest neighbor galaxy of this galaxy. So I call my galaxy as target galaxy, and the target galaxy has a neighbor, nearest neighbor. If the nearest neighbor galaxy, I don't know the morphological type of my target galaxy, but I know the morphological type of my neighbor galaxy. If neighbor is an early type, the probability monotonic increases as these two galaxies approaches. Okay? As my neighbor approaches to myself, then my early type fraction monotonically increases. But if my neighbor is late type, then as I approach my neighbor, I first tends to become an early type. Then at about 100 kiloparsec separation, then I tend to become late type as well. So this demonstrates the importance of distinguishing the morphological type of the neighbor galaxies. If you don't, people haven't found this and thought the neighbor gives negligible effect on the galaxies because they did not distinguish the morphological type of the neighbor. If we add these two, we just get a straight line and think the interaction doesn't give much impact. So, but actually there's very strong effect from the galaxy-galaxy interaction. So then we want to understand this x-axis better. So you can see the deviation deviation between these two cases start to occur at about several hundred kiloparsec. Then here's my target galaxy and my neighbor galaxies. I assume constant mass-to-light ratio to convert the luminosity of my neighbor galaxies to mass. Then I know the distance between these two. So using this distance and the mass of neighbor, I can calculate the local density at target galaxy attributed to the neighbor galaxy. So I change x-axis to that neighbor density. And this dotted line, these two dotted lines are the same as these two curves. Now x-axis change to the density, and you can see basically the same behavior. As you go to high density, that means you are moving left over there. As you go to high density, they are approaching. And this bifurcation occurs at about between 100 and 1,000 times the mean density of the universe. It's the density due to the neighbor. And at this density range, they start to diverge. So when they are well separated, they don't care the morphological type of the neighbor. The early type fraction of my target galaxy doesn't care the morphological type of the neighbor galaxy. But as soon as this density exceeds this critical density, then it depends on the morphology of the neighbor galaxy. The important thing to note is this density is the video density. So when my galaxy enters into the video radius of my neighbor galaxy, now it starts to be affected by the morphology of the neighbor galaxy. So there must be hydrodynamic interaction going on.
So is this dark matter density or?
Yes, it includes the whole density. So it's basically galaxy plus dark halo system. Yes. So here, I'm using two environmental factors. One is the neighbor morphology, and the other one is the neighbor distance, or the neighbor density. So I'm going to add one more.
Do you have redshifts for these galaxies, or?
Redshift.
Yeah, like,
Yes. Yeah.
so they're actually 3D distances you're quoting, right? It isn't like 2D distances.
It's 3D things, yes, basically.
But the R, I mean, well, like the radius, that's in projection or?
This is projected separation, yes.
But they're at the same redshift.
So I constrain the neighbor to have the radial velocity difference less than something, the redshift difference less than something. Okay?
So do you have estimates for the contamination by like projections on the outside? Or?
There should be some contamination, yes.
But do you have estimates for how much that is?
It's about between 10 and 30%, depending on the separation.
Right.
Okay.
But you could do this in 3D.
Well, he's saying that there is intrinsic peculiar velocity difference,
Yeah.
right? And that can be mixed with true difference in distance. So, but as you can see, there is such a large signal. This can be accidentally happening, right? And also, there's a physical scale involved. And as you see the brighter galaxies, you can see this bifurcation still occurs exactly the same scale. So I'm going to add one more environmental factors, which is the large scale density. So you see the blue dots are late type galaxies and red dots are early type galaxies. You have this large scale distribution of galaxies. You want to estimate some background density vectors, and we have the variable smoothing filter, which includes fixed number of galaxies. So we call this as rho 20. So this the contour shows the density field smoothed by this variable size filter, the low density regions and high density regions is closed. So in addition to the density due to the neighbor, we also have the large scale background density. And we want to see how the morphological type of galaxy is affected by these two density parameters. And now we are looking at these contours are FEs, morphology, the early type fraction contours. And the x-axis is rho 20, large scale background density. The y-axis is the distance to the nearest neighbor galaxy, normalized by the video radius of the neighbor. So one corresponds to about between 200 and 300 kiloparsec, depending on the luminosity of the galaxy. When the neighbor is an early type, you can see the contours look like this. If you compare this with the case when the neighbor is a late type, you can see basically at the neighbor separation greater than 1, it's more or less the same. Its contours are more or less horizontal, and the value is about the same. But at separation smaller than that, you can see the contours are completely different. So at fixed large scale density, as you approach the neighbor, my early type fraction probability monotonically increases. But here, it first increases, then it decreases. This is what we have seen before. At fixed neighbor separation, as I move from low density to high density regions, my morphology fraction, early type fraction monotonically increases. And when the neighbor is a late type, it also has the same direction. As I move from low to high density regions, morphology fraction monotonically increases. Early type fraction increases. So, but at large scale, the contours are basically horizontal, which means the dependence on road training doesn't exist. So the large scale density dependence occurs only when galaxies are close to each other. So we can make several conclusions. The local density due to nearest neighbor morphology depends on that, which is the vertical direction, and morphology depends on neighbor's morphological type, which is upper and low panel. And the background density dependence exists only within the nearest neighbor's visual radius, which means outside that, its contours are horizontal. Okay, some drawing like this. So this is my neighbor, and this is my target galaxy. And the target galaxy is far away, then there's no dependence on background density, this morphological type. And there's no dependence on neighbor's morphology. It's the same. So probably the interaction is only through the gravity in this case. But if the distance is now less than the video radius of the neighbor galaxy, so that they are like this, then it asks all three questions. How far these two galaxies are? And what is neighbor's morphology? Then where the system is located. So it all depends on three. I'll skip the luminosity part because this is another big question related with the mergers. Let's look at other parameters. I just showed you the morphological type. And now I'm showing you the color and the equivalent width of H alpha line, which is a measure of star formation activity, and the color gradient. Let's look at just one panel. This is the case when my target galaxy is a late type. I have a late type target galaxy. And it's a bit difficult, but the blue dots are the late types having late type neighbor. And the red dots are the late type galaxies having early type neighbor. And as this galaxy approach to the neighbor, depending on morphological type of neighbor, they start to diverge. And they start to diverge at exactly one video radius of the neighbor galaxy. And then, at about 5% of the video radius, they start to diverge. And this is the scale, this is the merger scale. So this corresponds to about 200 and 300 kiloparsec, and this corresponds to about 10 and 20 kiloparsec. So they physically start to overlap at this merger scale. So we find there are two characteristic scales in galaxy-galaxy interaction. One is the neighbor galaxy's video radius, and the other one is the merger scale. And the fact that they bifurcate implies the hydrodynamic interaction must be going on between these two galaxies inside this video radius. The center monotonically becomes bluer, or outside monotonically becomes redder. And probably center must be getting bluer because the color gradient monotonically increases for both late time neighbor and early time neighbor. So other structural parameters, concentration index and central velocity dispersion. And as galaxies approach, their concentration increases. this is inverse thing. So concentration increases, and the central velocity dispersion increases. Right? And the effect is stronger when the neighbor is a late type. This is because the late type galaxies move slower relatively to the early type neighbor. The early type galaxies move much faster, so they give less amount of tidal energy deposit. So that's why the late type galaxies gives more change in the structural parameters. So we got some understanding of this. And the question is, we used Sloan data, which is basically at z equal 0. Actually, it's 0.05 or 0.1, but it's basically 0. The current snapshot of galaxies. And we found the galaxy-galaxy interaction gives very strong effect on galaxy properties. Was it also important in the past? Or was the galaxy-galaxy interactions affecting the galaxy evolution for a long time? To answer that question, we looked at the galaxies at higher redshift, GOODS data, and Deep 2. And I'm not going to show Deep 2 because Deep 2 didn't show positive results. It's a lot more structured than this. It's hard to see. So here's the GOODS north and GOODS south as a function of redshift and the actual magnitude. And this is the magnitude cut approximately. We collected all published redshift data. And the redshift completeness is about 85% for GOODS data. GOODS north is slightly higher. The south is slightly lower. And Deep 2, the completeness is about between 50 and 60%. And if the redshift completeness is low, we are not able to find the true neighbor, because half the times I choose wrong ones because my data misses the galaxies. So that's why we don't get positive results from Deep 2, but we get results from GOODS data. And we visually classify galaxies. There are about 4,400 redshift in GOODS north and south. And you look just at the all image. We made these color images out of these 4 HST images. And this is the late. Do you agree? This is a little subjective, but I think we made a very good, very reasonable classification. And the result is, yes, even at z equal between 0.4 and 1, we still see this bifurcation, depending on the morphological type of the neighbor. The error bar is much large, so we are not sure where they are exactly bifurcating. But we can clearly show that there is a statistical difference between the cases with early time neighbor and late time neighbor at small separation. So this proves the galaxy-galaxy interaction have been an important factor in galaxy evolution for a long time. Now, galaxy interactions in the cluster environment. So we found Abel clusters in SSS area and looked for the member galaxies and also the all galaxies within 10 times the video radius of the cluster. The member galaxies were found to calculate the video radius. Then using that video radius, we go out to 10 times the video radius of the cluster and get all sample within that subpart. in velocity radius diagram. So I think it's basically the galaxies are within plus minus 1500 kilometers per second, I think, from the center of the cluster. And this is the result. Again, the contours show the early type fraction. And the x-axis is now, instead of rho 20, which is the large scale background density, x-axis is the distance from the cluster, normalized by the cluster video radius. So 1 corresponds to roughly maybe 1.5 megaparsec. It depends on cluster, between 1 and 2 megaparsec. And y-axis is again the distance to the nearest neighbor galaxy. So this is the large scale environment, and this is the very small scale neighbor environment. At cluster central radius larger than the video radius of the cluster, the contours are basically horizontal. So for the early time neighbor and late time neighbor cases, in both cases, as you approach, as the galaxy approaches to the neighbor, the early type fraction monotonically increases when the neighbor is an early type, but when the neighbor is a late type, it first increases, and at about this scale, which is 1/3 of the video radius of the neighbor galaxy, then it starts to decrease. So this is the behavior we have seen before. Surprisingly, there is no effect from cluster. It's absolutely horizontal. As soon as you enter this range, things change. The contours are almost vertical. When these galaxies are not too close to their neighbor, the contours are basically horizontal, it's vertical, which means the morphology is completely controlled by the cluster, or cluster environment. So there is a sharp transition at scale roughly equal to the cluster video radius. And that transition scale actually depends on the tracer galaxies. This is the galaxy I have just shown you. And when we look at brighter galaxies, the transition occurs at smaller cluster centric radius at about 1 and 1 times the video radius. For fainter galaxies, the transition occurs at larger scale, about three times the cluster video radius. So it's basically the smaller ones have transition at larger scale, and massive ones have transition at small scale. So we found that. And we look at other physical parameters. So again, this is the color, and this is the star formation activity, and this is the color gradients. There are many things, but just to look at one panel. This is the case when my galaxy is a late type, but this galaxy has an early type neighbor, so LE. And this LL means my galaxy is a late type, the neighbor is also a late type. So I have four panels actually, vertically. The early type, I didn't show the early type because their color don't change much. But late type color, they change a lot. And you can see this is almost horizontal. And this is the one video radius of the neighbor, which is maybe about 300 kiloparsec. So this is, again, almost 100 kiloparsec. And you can see the cluster is not doing much. It's basically the neighbor galaxy, which determines the color. So this demonstrates the importance of neighbor even inside the cluster. This shows the outskirts of galaxies getting redder as galaxies move inside the cluster video radius. But what is the important thing is this: the contours are nearly horizontal. colors and star formation activity are controlled by the neighbor galaxies. Which means, so when galaxies enter in the cluster, they move fast. So probably the tidal interaction is very short. And that's why people thought galaxy-galaxy interactions are not important in cluster environment. But hydrodynamic interaction can be even stronger. They move very fast. So even though the tidal energy deposit is small, the hydrodynamic effect can be even stronger in cluster environment. And that seems to be the reason. The structural parameters, look, it's slightly different. It's more or less vertical in this case. And the transition occurs again at about cluster virial radius. So this means here I want to emphasize there is a sudden transition in structural parameters of galaxies at the scale of cluster virial radius. So far, I'm showing you a lot of results. You may be confused, but I just want to emphasize the importance of the neighbor interaction, galaxy-galaxy interaction in the cluster environment. And there is a sudden transition at cluster virial radius. And you can give some grading to various ideas. Who is actually doing what? The one which is affecting the galaxy properties can be the cluster itself. It could be cluster gas or cluster tidal force or something. Or it could be the neighbor galaxies. So the one game I did here was it could be cluster or neighbor galaxy. Cluster or neighbor galaxy. And it could be cluster's gravity or cluster's gas or neighbor's gravity or neighbor's gas. So I can give some gradings. And I see none of them got 100 points. Okay. For example, for the concentration index, this is structural parameters. Gas can change the structural parameters. They can change the color. They can strip the cold gas on the structures. So they get crosses here. For color, the fact that these are horizontal and the direction of change, the direction changes for different neighbor morphological type cannot be explained by cluster gravity or the cluster gas or neighbor's gravity. It should be neighbor's gas, which is responsible for that. So I give this kind of gradings, and this is the result, for example. So probably all of them are responsible, not just one. But you can see what's going on. So to summarize the key results and give some interpretation. First, we found the effect of neighbor galaxies are very big and reaches out to a megaparsec. And previously thought it was marginal and effective only within much less than 100 kiloparsec and mostly at separation smaller than 30 kiloparsec. But we find that's mainly because people did not distinguish the morphological type of neighbor galaxies. They just added these two and got straight line. And we found two characteristic radius. One is the virial radius of neighbor, which is this, and the other one is Moses scale, which is 0.05. Okay. And the fact that these are bifurcating can be only explained by the hydrodynamic processes between the interacting galaxies. And also the fact that this is dropping suggests the morphological transformation is possible from early to late type galaxies. For example, well, this demonstrates the mass transfer between galaxies. Oops. Here's a simulation by the Cullinan et al. To simulate ARC 104. And they did not intend to simulate this system, but when I read this paper, I thought I saw this system before. And so I went to the SSS and found this one again. Could you turn off the light? of that? Okay, you can see this tidal bridge and this tidal tail and this little pattern, which is, you can see it's almost the same. So maybe. And this simulation demonstrates the mass transfer. These red dots originally belonged to these late-type galaxies. Now some of them are over here. And the hot gas particles, which originally belonged to these early-type galaxies, and some of them are over there. So this demonstrates the mass transfer. This one suggests the morphological transformation from early to late-type galaxies. This galaxy seems to be originally early-type galaxies, and now it's getting cold gas from its late-time neighbor and got to wings, which is very unusual as an early-type spiral, because early-type spiral usually don't have this kind of very blue disk. This is extremely big bulge. It is a late-type galaxy. So it's more natural to explain this as a case transforming from early type to late type. So if the gas coming from the neighbor directly goes to the center of early type galaxies, the early type galaxy overall becomes blue. But if the gas carries enough angular momentum, then they can form a disk and transform the early type galaxy to late type. And this is one interesting case. There's a late-type galaxy and the early-type galaxies, and in between there's an early-type galaxies, and it has an arc only on one side. So it seems that this galaxy is hesitating where to go, because this big early-type galaxy is trying to make this one back to early-type, but this galaxy is trying to make this one as late-type. So there are some cases. These are not very common, but you can find such examples. And the morphology density relation, which is best measured by this plot, this is basically the morphology, early type fraction, and the large scale density, and the luminosity relation. So at fixed luminosity, even if I fix the luminosity, as I move from low to high density regions, the early type fraction monotonically increases, and the halting scales as luminosity increases. But now we are saying that this increase is basically because of the statistical correlation between large-scale background density and the distance between galaxies. As we move from low to high density regions, the mean distance between galaxies is getting smaller. So they are having more influence from neighbor galaxies, and the more frequent interaction with neighbors. So morphology density relation is due to the galaxy-galaxy interaction rather than the large-scale environment. And that's our claim. The cluster environment, we found sharp transition of galaxy properties at about cluster virial radius. And this transition was found for morphology and color gradient and the structural parameters like concentration index and central velocity dispersion. And we can see the morphology density relation is not working, because if we see the projected number density distribution of galaxies, these are early type galaxies from the center of Abel cluster, and this is the number of late type galaxies from the central cluster. They monotonically decreases, and from the 1 times the virial radius to 10 times the virial radius, there is almost 1 order of magnitude number density drop. But you see, the early type fraction is basically constant. If we don't distinguish this, then we basically move this way. And if we cross the contours like this, and we think there are more spirals, more late types, as we move away from the center of clusters. But if we take into account the fact that as we move to the low density, the mean distance between galaxies are getting larger, if we subtract this fact, then it's basically the same. So there is no large-scale density environment affecting the morphology. So the morphology density relation is not working. And we can also say the pre-processing is not working beyond the galaxy-less interaction. If there are groups, inside the groups, the distance between galaxies are closer, so there's more pre-processing because of that, but not the group itself, not because of the group itself. And this transition depends on the luminosity of galaxies, and this is probably the mass segregation. And it may be, so what's happening is what we are seeing here is basically the bound galaxies inside the clusters, and they have orbital motions and interact with the clusters and neighbor galaxies over and over again. And massive ones have smaller orbit, and the small massive ones have larger orbit. And that may be why the transition scale depends on the luminosity. And I'd like to emphasize the importance of neighbor galaxy. You can see this horizontal line. The neighbor galaxy is still giving a big impact on the physical properties of galaxies, and that must be hydrodynamic interactions. And previously, people were asking whether morphology radius relation or morphology density relations are fundamental, and now we find it is morphology cluster-centric radius and neighbor environment relation, which exists in cluster environment. So the conclusion is, I'm just repeating, we found the morphology and the galaxy properties depend on nearest neighbors distance and nearest neighbors morphology and the large scale density when they are within the cluster virial radius. And we found nearest neighbor galaxy gives critical effects on galaxies in both field and massive clusters. And we found critical distances, the virial density of the nearest galaxy, the Moser scale, and the cluster virial radius. And the cluster is like a giant elliptical the early type galaxies, if we compare this. I mean, we think now that the relation that exists in cluster environment is the morphology, radius, and the nearest neighbor environment relation, which includes both distance and neighbor morphology. Thank you.
Questions?
Okay, so I didn't follow the last point you were making about about the nearest neighbor being important even inside of cluster halos. So can you say it again? I didn't follow the argument.
Yeah. So the sum of the galaxy properties like star formation activities, they show this kind of the dependence on the cluster centric radius and so at fixed cluster
Is that a
centric
strong
radius.
gradient? I mean, is that what you're saying?
Hmm?
So you're
Well,
finding a gradient, I guess, like
Yes, yeah.
vertically,
The
but-
contours are horizontal. So at fixed radius from the cluster, as I approach my neighbor, my color changes a lot, and my star formation activity changes a lot.
Is that a lot, really? I mean, going from like, what, 10 to like 12, I don't know. Is
It's
that a
not-
large change?
It's not small. But, well, if you compare the change horizontal along the horizontal direction, you can see that. At fixed neighbor separation, as you move from the center of cluster to outside, you basically have no change.
But in the bottom row, it seems the contour lines are nearly vertical.
This one?
Yeah.
In this case, I didn't say that, but at this cluster centric radius, now the second and third nearest neighbors start to matter. And as we approach to, right now, this galaxy has a late-time neighbor, but as you go to the center of the cluster, the second nearest and third nearest are more likely to be early type galaxy. So at a little larger tail separation, that is coming in. But other than that, it's basically the neighbor, the nearest neighbor, which gives this horizontal contour.
So remind us again the difference between the top and the bottom. The top is the nearest neighbor is an early type galaxy.
This one,
Yeah, and the
Yeah.
bottom one is that the nearest neighbor is a late type.
yes. But at small cluster centric radius, you can think the second and third nearest neighbors are basically all early type galaxies.
But even in the outskirts, the blue line is still more like vertical.
This one?
Yeah.
Yeah, it's important to see the direction of the contours, but also you have to see the gradients. Basically, it says there is basically no gradients. Okay? So, it's almost flat. The star formation activity almost doesn't change. And at this separation, it starts to drop. Yes. That's what it's showing. So the fact that these are noise outside, this means that does not mean they are really noise. It means it's more or less constant. And when the contours are very close to each other, then there is a strong signal.
Now you also showed a plot where you had the separation between the nearest neighbor being elliptical and the y-axis, whereas if you had a nearest neighbor being a early type and late type galaxy, you went up and then came back down. Right? Can you put that one back?
That's seen in cluster as well.
Yeah.
So it rises and drops, but it monotonically rises.
Right. So I would have said that. Right. If your neighbor is a early type, you can make the argument like fun. If the neighbor is a spiral, still star forming spiral, it's got gas in it. It hasn't, maybe going through the first interaction. If it's a late type guy, then you might say, well, what happens is it's the nearest neighbor that's already gone by the close interaction, you've used up a lot of gas, or something along those lines. Right? In other words, if you got a physical interpretation for this.
Yeah, the mass exchange, according to the simulation, the mass exchange usually occurs after the nearest approach. So,
Well, is it there a mass exchange, or is there, you could have a starburst, for example, without any mass exchange?
no, I don't think that's the reason, because if it's only gravitational force, the direction of change will be the same for both early type and late type galaxy. Because
No, because suppose you had two gas-rich galaxies, right? And they were having a first interaction. Okay, there's still a big reservoir of gas around, and you can make stars. But if you got through many interactions, right, then your nearest neighbor is going to be an elliptical, and you're going to be elliptical, right?
you're saying
You see this difference between having, if you're just told that the neighbor is an elliptical or a gas-rich galaxy, right? Then you say it's small distances. You see that the neighbor, gas-rich galaxy means you're also a gas-rich galaxy.
Yes.
Okay.
And the problem is that difference comes exactly at 1 video radius of the neighbor. This is hard to explain by that kind of accumulated effect.
Why?
I mean, how can you maintain this sharp transition scale if galaxies are coming in and go out, and then there should be some smooth transition in the variation.
Well, not if they only need 1 or 2 passages to use up all their gas.
Well, it's not clear whether the galaxies are just passing just one time, and if they are just whenever they meet, they merge.
Well, if they come close enough, right? You were saying inside 100 parsecs or kiloparsecs, right? I would have thought if they came within 100 kiloparsecs, then they will produce a starburst.
Yeah,
Okay.
that's about this scale, 0.1.
Yeah,
It's
exactly.
smaller than that.
Yeah.
And that's probably why it's diverging.
Okay, so that's what I'm getting at. So keep going back here. You showed that plot.
Cluster case?
That plot right there. No, you just went by it.
Cluster.
The early fraction versus radius with the
Early, yeah.
two types of neighbors.
So I could slow down.
Like your second plot or third plot.
Yeah, very early on.
The,
At the beginning.
the very
Yeah.
the very beginning of that
There,
plot.
that
That's
one.
one. Yeah.
Okay. So like on the left there, right? So you've got a large radii. Being told it's early or late doesn't give you any information. It just says that the closer you are, the more likely you are to be an elliptical. But
Yes.
if you get really close, then the information from the neighbor actually tells you something. The neighbor, if it's gas rich, tells you you're gas rich.
Right.
That's what that plot says. Right?
Mhm.
Whereas if your neighbor's gas poor, then you're gas poor. It seems to me a really simple explanation for that is that, if your neighbor's gas poor, it's because it turned all its gas into stars. And you've done the same thing.
Mhm.
Okay? And conversely, if your neighbor's gas rich, then you haven't had a chance to turn your gas into stars either. Even though you're sitting here at 0.01 kiloparsecs or megaparsecs.
Yeah, we can start with that idea, but there are many more things to explain.
Well, but what's the basic explanation of that plot on the left? What's causing that in your current view?
So that's why I'm saying they are hydrodynamically interacting.
But is it that they're exchanging gas? When you say hydrodynamically interacting, what do you mean?
Yeah.
What's the physical process? So you showed one example where they're actually exchanging gas between a gas-rich guy and a gas-poor guy. Is that what you're saying is going on? That's a hydrodynamical interaction.
Yeah, I meant they are exchanging gas.
They're exchanging gas.
So when the early type galaxies approach, it carries hot gas, hot halo gas,
Right?
and that's probably pushing away the cold gas or ionize the cold gas on me.
So it's stripping the gas out of the other
Yeah,
gas.
it's like basically galactic scale stripping. And when my neighbor galaxy is a late type, and there must be some cold gas transfer in this. That's
Well,
why.
you could make the argument that they're both early types. There's no hot halo. They don't interact hydrodynamically, and that's why you don't see, this elliptical fractions of both.
Actually, this has to be explained together with the luminosity evolution, which is the merger, actually. I skipped that part. So in high density regions, the interaction and merger frequency is higher. So as they transform morphology, they also transform luminosity as well. So yeah, that part of I skipped that. Yes.
Yes, we should stop here. We can continue the discussion about cookies. So let's thank Jean-Laurent